Okay. Good afternoon. Lights went out. You guys aren't as much fun as the fifth graders. You're not in costume. Okay. Up on the screen is where we left off last time with this beautiful example of all the prime numbers inside your computer. And I want to look more closely at this business of infinite streams and start by saying, remember when I first did that prime question mark example, I defined a little helper function called range, which looks like that. And then we just made a tiny change to it. That's all. Basically, I changed cons to constream. And yet, that tiny little change makes an enormous difference in the way the program runs, right? In the order of events that happens in the computer. If you're trying to trace through the program, and if you don't understand how constream works, you're going to get a completely wrong idea of the order in which things happen. But that's okay as long as you're doing functional programming, because although your completely wrong idea isn't the truth about the sequence of events, it gives you the same answer as what really happens. And in functional programming, we only care about the answer. We don't really care about the intermediate steps, because something that happens in this step isn't going to affect something that happens in that step. And then we can make what looks like a huge change in the program, namely this. We can make it a procedure with no base case, and it still works. In fact, I don't even need the variable 2 anymore. I can say define ints from to be constream from ints from plus from 1. And then I can say show stream of, for example, ints from 27. And I get the infinite stream of integers starting from 27 and counting up. So in form, what we have here is a recursion with no base case. Something a little bit like this, but not quite so dramatic, happened when we did tree recursion, when I wrote tree map. And there was what looked like a recursive call, but it wasn't the direct recursive call. It wasn't tree map calling tree map recursively. It was tree map calling regular old map with a function that had tree map in it, lambda of child, tree map, blah, blah, blah. And because of that, instead of one recursive invocation, we got a variable number, 0 through however many you want, however many children this node has, recursive calls. So that's a program arrangement in which the sequence of events is not directly obvious by reading the code. You have to think hard about it. But if you forget about the sequence of events and just think about what answer am I getting, it's much, much easier to understand tree map. And the same thing is true here. Never mind the sequence of events. This says ints from 27 is the same as constream 27 ints from 28. And that's true, right? If you want to make the infinite set of all the integers starting from 27, that's 27 plus all the integers starting from 28. And so our program gets the right answer, and we don't have to sit and think about, wait a minute, what possible sequence of events can there be to make this work? Because it's a recursion with no base case. Is it a recursion with no base case? Well, obviously not exactly. What really happens is constream is a special form. It doesn't evaluate that second argument, the so-called recursive call. And so that call doesn't happen until we force the promise by saying stream coulter of this stream. Every time we say force by saying stream coulter, which does a force, we move one step along in the computation. And then we find another constream. So what would be the second step is not forced at this moment, but is waiting as a promise for another stream coulter to happen. Sorry, I'm deathly ill. OK, so a beautiful thing, a recursion without a base case, and it works because of this funny way of thinking about things. I wanted also to go through this business of implicit definition of streams and look at how we got this value for integers, because that's something that people find confusing. So I think last time I convinced you that ones, which we made by saying constream 1 ones, is an infinite stream of ones, right? Well, what about integers? Well, we know what the first number in integers is because the definition says constream 1 something or other. So here's a 1. And for reasons that will become apparent in a moment, I'm going to write down integers again, starting one space to the left. Because what's the second number in integers? Well, it's the stream car of 1 plus the stream car of integers. And that's 2. Oh, what's the third number in integers? It's the second 1 plus the second integer. What's the fourth number in integers? It's the third 1 plus the third integer. So we come up with the integers on a sort of just-in-time basis. It's like being a Japanese car manufacturer. We construct integers just in time for the next plus to happen. OK? Any questions about that? So again, as with trees, the right way to think about this stuff is you spend a little bit of time carefully tracing through things the way I just did to convince yourself that programming in this style can work at all. And then once you've convinced yourself, you don't do any tracing at all. You say, OK, suppose I have the infinite set of ones and the infinite set of integers, and I write them down one underneath the other, and I add them up. What do I get? And the answer is I get 2, 3, 4, 5, et cetera. And if I constream a 1 in front of that, I have the integers. OK? So you think about it, pretending that you really do create all of them at once. Yeah? No. The question is about how stream map works. Do you remember how plain old map works? It says plus call the function on the car, and then a recursive call to map for the coulters. It's the same here. So I'm taking advantage of a feature that's in map also, which is that you can actually have more than one data list argument. You can give map, let's say, 4 arguments altogether, a function and 3 lists. And then the function should take 3 arguments. And we take all the cars and we give those to the function, and then we take all the catters and give those to the function, and so on. Yeah? Right, each recursive call to map makes one call to plus with car of its arguments, with car of all of its arguments, okay? Now, all of its arguments are going to be first the entire stream, and then next recursive call, it'll be the cooters of the entire streams, the stream cooters. So in each recursive call to map, we call stream cooter on all the stream arguments. And that gives us one more value, okay? And then we use those values calling whatever the function is, in this case plus. Plus is nice because it takes any number of arguments, so we can do tricks like this easily. You don't need a special plus with 2 arguments or a special map with 2 arguments. It all just works. Okay, other questions? All right. So a reminder, as somebody said last time, if you do mutation in the functions that generate streams, peculiar things will happen that you won't like. And there are some homework exercises in which you do that on purpose to see what happens, to try to figure out what happens. And the whole point of those homework exercises is to convince you never to try it again. But only use streams with functional programs. Yeah? What are the advantages and disadvantages of streams versus local state? Thank you. That's a great question. To put that question in another way, why are streams in Chapter 3? Right? Because Chapter 3 is about mutation. But even before that, Chapter 3 is about modeling inside the computer a system that changes over time. And one way to model a system that changes over time is object-oriented programming with local state variables and methods that, that set bang them, right? This is another way, and let me show you how that works. Can't type. Okay. Show stream, just to make it interesting, stream map m to x times xx user stream. Okay, so I type all that, and I hope I typed enough close parentheses. Yeah, I did. And it sits there. And I type a number like 10. Interesting. Still sits there. Uh-oh. Did I do something wrong? Nope. Huh. Why didn't that work? I think that should have worked. Oh, because I'm an idiot. Whoops. Oh, maybe they're not going to come out until I finish everything. What? Oh, look at that. Oops. Ah, okay, thank you. Let's try this again. That's what comes of making up examples on the fly. Oh. Ah, interesting. Okay. So nothing printed out until sorry, whoops. Yeah, I needed, right, 10 things to get it to come out. I was hoping they would print a little at a time, but they didn't. See, if I just say show stream, user stream, let's see what this does. Yeah. Oh, well. Anyway, you get the idea, which is the user stream procedure returns the stream of everything that the user is going to type from now on. Okay? Well, now suppose we want to represent your bank account. So I'm going to say define my account. And I'm going to start with a $100 initial deposit. Okay, so I have a $100 deposit. Now I'm going to deposit $1,000. Then I withdraw $100. Then I deposit $10. Then I withdraw $7. Then I deposit another $1,000. Okay? So the stream my account is the stream of all the balances that my account is ever going to have from now to infinity. And we can write programs using it as if we had it all at once. So, for example, when I defined my account up here, I'm assuming that I have all of user stream, all the deposits and withdrawals that I'm going to make until the end of time. And I say, okay, the running balance on my account is start with the initial balance and add the deposits and subtract the withdrawals. Right, so deposit is a positive number, withdrawal is a negative number. And I add those things in. And that gives me my entire bank account for all time. So you see that this is a way of modeling time-varying state. Functionally, I can do functional programming with this thing. So here's another example. Oops. Wah. That's what I meant. Okay? So this is an infinite stream of random digits. And if I want to do some program that involves randomness, instead of going through it step by step and sort of asking for one random number each time, I can take this as given. And of course, the programming that makes random stream work is not exactly really functional if you look inside, because random isn't. But random stream is, because I'm only going to call it once. I'm going to say define random digits to be random stream, call random stream. And now I can, I hope, just some random digits. So if I do that again, I get the same set of random numbers. So this infinite stream, from now on, if I just take it as something I set up at the beginning of the program, it's always the same value, and I can use this value in a program that says, take all these random numbers and do something or other with each one, calling map, in a way that uses random stream. Okay? So, yeah. Why do I have to call it? Well, I'm not exactly calling a stream. Thank you for asking. What I'm doing is writing a procedure whose output is a stream. And the reason I have to do it that way is if I just define, if I said, well, let's do it. Define rands, const stream, random 10, rands, like that. Okay? What am I going to get? Okay, midterm 3 question. What am I going to get? Yes? Good.
Infinite stream of the same random number?
Yeah, I'm going to get one random number repeated infinitely many times, because it's the same thing I did with ones. It's const stream a particular value onto this same stream. Whereas when I write a procedure, if you compare that with this definition, every time I cache in a stream cutter, I'm calling random stream again, and so I'm calling random again. Okay? And the same is true with user stream. I have to keep calling read, otherwise I'll just read one number and get that over and over again. Okay? So it's sort of the price I have to pay for introducing non-functional elements underneath the table. Yeah? Oh. Why did random digits give me the same stream every time? If it doesn't exactly, if I call random stream over and over, I get different ones. But I said, define random digits, and then I call random stream. Okay? So now that fixes my first one. It kind of tethers the whole thing. So I'm having one particular set of calls to random. So if I show stream random digits, if I, oops, control. If I do that again, I'm not calling random stream again. I'm just redisplaying the same variable, random digits, that contains the call to random stream I've already made. Yeah? Oh, yeah, good point. You're absolutely right. I've forgotten to teach you something. which is I lied about how it works. I told you that streamcar is just car, which is true. And then I said, that when we call stream cdr, we just take the cdr, which is a promise, and force it. But really what we do is that. The first time we call stream cdr of a particular pair, we remember the value that we got. And that's done for efficiency reasons. Suppose that we're computing some stream that's computationally expensive. We don't want to recompute the same value. Remember, way back at the beginning of the semester, when we talked about applicative versus normal order. Scheme uses applicative order. And we looked at the case times xx, and then we define square x times xx. And what if you call square of something that's computationally expensive? In applicative order, you only compute the argument value once. And in normal order, at least in naive normal order, you have to compute it twice. Well, we avoid that using memoization, because now we know a way to avoid it, which is this idea of memoization. Right? And by using memoization, we can have the reordering effects of normal order, and we also have the efficiency of only computing things once.
I think maybe force will automatically keep track of which promises have been forced freely.
Right. OK, so what he's saying is, I don't have to write memoize right there. Instead, what I do, and you're absolutely right, is the definition of force does the memoization. OK, so when you call force of a promise, and in STK, you can actually see that. Because you get number sign, promise, blah, 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 or number sign, forced promise, value. So it shows you that it remembers whether you've done the forcing or not. Somebody over there? You gave up. You answered it. OK. Yes. You're next. OK. Question is, if I only want my current bank account balance, why do I need the stream of all my future balances? And again, the answer is, functional programming has all these wonderful properties that you can reorder things to your heart's content, you can parallelize things, and everything still works. Whereas we're going to shortly look at some of the complexities that come up when you try reordering things or parallelizing things that do mutation. So this is a way to have our cake and eat it too. The problem with functional programming is that it doesn't have any sense of time in it. It tells you the answer to some question. Okay? Well, if what you want to know is your bank balance right now, I can't exactly say that in functional language, because there's no notion of right now in functional programming. I only get that when I have sort of a sequence of steps, and I go through and I change the balance, and now I can say, OK, what's the balance after that change? But if I have all your balances from now on until forever, then I'm back in the world of functional programming. I can do computation. For instance, I can say, suppose this account is a savings account. All right? So it gets such and such % interest, compounded monthly or daily or however often it is. I can write a little program that takes user stream and the initial value, computes the value by adding in the deposits, and then computes the value plus interest, compounded. And I can do that functionally. I can say map a function that takes this value, multiplies it by 1.001 or whatever it is, and that's the next value. And I can apply that function I can interleave that with your deposits and withdrawals. I have to, in order to get it exactly right, I have to do something a little more complicated, which is keep, for each deposit and withdrawal, a timestamp. So I know when to do the interest calculation relative to all the other things that are going on. But again, the sort of one sentence point of all that is that I can model something that changes over time, namely your account balance, and still do functional programming. Because if you kind of squint your eyes and forget about the impossibility of it and say, OK, here I can predict the future. Here's the stream of all your account balances every minute from now till the end of time. OK? Well, now I can do functional programming on that, because that's something that doesn't change over time. Right? Your instantaneous balance does change over time, but the whole trajectory doesn't. It's a little bit like the relativistic view of trajectories, where instead of having 3 dimensions and a snapshot where here's the ball I'm throwing, and here's where it is now, here's where it is now, here's where it is now, here's where it is now. Instead of that, we have a 4-dimensional plot of a graph. And that graph represents the entire trajectory of the ball. Right? So you do that in physics 7C, I guess. And we're doing something like that with your bank balance. Okay? Because for the same reason, it simplifies the thinking about it in doing further calculations. There was a hand up. Yeah. Yeah. Yes. The question is, didn't we have to change delay and not just change force? Well, sort of. What we're going to do is delay will produce a data structure that has a true or false flag. Has this been forced yet? And then either the function of no arguments that computes the promise, or the value that we got. Right? Yes? Right. How did we implement constream if it's not part of standard scheme? We used macros, a feature of scheme that we don't really get into in this class, but you're welcome to read up about. Essentially, it's a way of saying, I'm defining this thing to be a syntactic keyword, the same as cond is a syntactic keyword, or lambda is a syntactic keyword. And when you see an expression that starts with this keyword, we basically call a function that turns it into a different expression, and then we evaluate that. So we just turn constream AB into cons A delay B, and then evaluate that. Okay? And that's something the scheme lets you do just for situations like this. Other questions? Yes? Oh, right. Memoize versus random digits. So the thing we're looking at up on the screen. Remember what showstream does. It takes the stream that you give it, starting from the beginning of the stream that you give it, and it keeps calling stream cdr 10 times, or however many times you tell it, or until it runs out. And then call stream car to get the values in those pairs. Well, if delay didn't memoize, then calling stream cdr again would compute a new random number. So really, technically, if we didn't memoize, I'm pretty sure this is true, what I would get is the first element of random digits would be the same every time. But all the other ones would be different because I would call random stream again, and that means I'd call random again. But because of memoization, once I've forced the promises in the first pair and the second pair and the third pair and so on, those promises remember the value that I got. So the second time I call showStream, it says, OK, give me stream coder of this stream. And the promise says, oh, yeah, I've already been forced. And the value I got was the stream 663, da, 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 da. OK? And similarly, the next one says, oh, yeah, I have the stream 638, blah, 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 and so on. OK? Yeah? Right, since they're not forced at the same time, the homework problems that you're going to do about this actually put a print in the function that you call, in the coder of the stream, in the promises that we're making. And so it prints out the first time you force that promise and not afterwards. And so when you do those exercises, you'll see how it plays out. OK? Yes?
You said that delay,
When
when you delay a procedure call, it checks whether that procedure is called the time.
you force a procedure, a promise, not when you delay it. When you delay it, it just sets up the data structure with the flag so that it can tell. It's force that checks. Is this the first time I'm forcing this promise? Or is it, have I already forced it? Does that clarify your question? I interrupted you in the middle. Does that answer what you wanted answered? If not, ask it again. When you delay, you don't delay a well, I mean, you could delay a procedure call, but you can delay any expression you want. When you delay the expression, it makes it an abstract data type called a promise. And the pieces of the promise are lambda of no arguments, your expression. So that remembers what expression you're trying to delay, and also remembers the context in which you're doing the delaying. So we know the values of variables, right? And the other thing that's in that promise data structure is a value that starts out as false and later becomes true that says, have I been forced yet? And the first time you force that promise, it makes a new data structure where the flag is now true. And instead of the lambda of no arguments expression, what we remember is the value that we got the first time we forced it. OK? Yeah, the code for how promises are memoized is in the book. So you can read all the details there. But that's the essence of it. Okay? Oh, thank you. Just what I wanted to know. OK, what haven't I said? Oh, yeah. So delaying stuff lets us build these cool infinite data structures. And it's efficient because of memoization. So why doesn't Scheme just use normal order? Let's go back to that question we asked in week 1. And the answer back in week 1, before we learned about memoization, was that it would be inefficient because we'd have to recompute things. But now we see that we can memoize expressions. So why doesn't Scheme just use normal order? Now let's not always see the same hands. Yes? Yeah? Memory usage. Good answer, because we have to remember all those values that we forced. But no, there's a Yeah, I know. It's true that we have a lot of things sitting around memory, and you have to be careful about that. But there's an even better answer than that. Huh? Yes? Yes. Scheme is a language that tries to support multiple programming paradigms. So as you've seen, we can do functional programming in Scheme, but we can also do object-oriented programming in Scheme, which involves mutation. If we did normal order, mutation would not work very well, because we would make a promise, we would change the value of some variable that that promise needs to use, then we would cache in the promise and get the wrong answer. Okay? So once you're allowing mutation, you're stuck with applicative order. But there are languages in the world that are purely functional programming languages. A couple of the well-known ones are ML and Haskell, are two purely functional languages. There is no mutation operation. And indeed, those use normal order. And so plain old lists can be infinitely long. You don't have to say stream, to invoke this special thing we invented. It just comes that way. So if you have a purely functional language, then it makes sense to have it be normal order. But if you're going to have a mixed mode language that lets you do functional and non-functional programming, then you'd better use applicative order, or else people are going to be surprised by the results of reorderings they weren't expecting. All right, so this is all stuff to keep in the back of your mind when you're thinking about the question of why is there more than one programming language? Why hasn't everybody figured out already that Scheme is the best one and get rid of all the other ones? You're supposed to laugh. Yeah. And one of the answers to that is that some people aren't very smart. But another answer is that there's more than one way to program, and and all the languages are equivalent in the sense that if you can write a program in one language, you can write it somehow or other in any of the other languages. I mean, it's possible to design languages that aren't that powerful, but every programming language you've heard of is equivalent in what computations it can do to every other language. But some things are easier in some languages than others because they promote particular styles of programming. And that's why there's still room in the world for different languages. Okay? Or at least that's one answer to why there's still different languages, and it hasn't all shaken out yet. And by the way, sometimes the reasons are big, powerful idea programming language things like normal order evaluation or functional programming. And sometimes they're a little, good at handling Unix file system files, or good at drawing animations with multiple characters up on the screen, or that kind of thing, where there's some interface to the real world that they did a good job of in a particular language, and that's why people use it. But anyway, okay. Time varying information did that. Infinite streams did that. Memoization did that. Reordering did that. Okay. Any more questions? Last chance. I don't see any. Okay, have a good weekend.